A very good afternoon to all of you. Good afternoon, Abhinav. Good afternoon, Pratham, Nimishka, Devesh, Rishabh, Jason. Let's start with today's work. We are in chapter 6 to remind you. We have almost done all the discussion topics in the section in this chapter. Some of the topics, minor topics here and there, I have left, and please go through them when you go through the chapter. So that's how we will go ahead. In this class today, I'm going to talk about loudness and duration. Remember, we were speaking about loudness in the last class. We talked about the loudness scale and the perception of sound at different frequency levels. So today we are going to talk about loudness and duration and our adaptation to impulsive sound. You know that it's harmful. Let's see what is there to talk about that. And then we will take up some of the problems. So going ahead, loudness and duration. So the key question arises that does the ear take some time to sense the loudness? The question is how quickly or how slowly does the complete intensity of sound is realized or perceived by the human ear? Does it happen instantaneously or is there a time gap? Now, what experiments have shown that ear takes some time to sense the maximum loudness. The loudness grows with duration. So even if your stimulus sound is fixed in intensity, your response to the sound will vary with time. So your input intensity is fixed, but you will achieve the maximum loudness perception in some period of time. So basically, what ear seems to be doing is accumulating the data and then averaging out or adding it up to give you the maximum loudness. Typically, a graph of relative loudness levels versus duration that it takes to build up is looks like this. I'm focusing on the pure tone. Pure tone is a pure sine wave. You can see that this scale is in milliseconds. It's a very small time, but yes, it is some time. So in 10 millisecond, if it goes to minus 15, and in 100 millisecond it goes to minus 5, and maybe around 150 millisecond or 200 millisecond. Remember, the scale is logarithmic here. This is 100, this is 1000. Maybe around 200 millisecond, the ear will achieve its maximum loudness perception. So the maximum loudness perception that the ear will achieve is in around 200 millisecond, and that will happen. I mean, that is what this graph depicts. So all throughout in this graph, the input pure tone has the same intensity. That is remarkable. You are not changing the input intensity, but how loud does it perceive, that is changing with time. And what it shows is as the time increases, the intensity increases. So that is what the basic idea is. The loudness perception increases. So that is with the pure tone. If it's a noisy tone, broadband noise, then the experiment result shows that it takes even longer. So it may be around 500 millisecond or something for the loudness to build up from its minimum value to its maximum value. After that, since the input tone or the stimulus has a constant maximum output, after this point onward, the maximum output remains constant. It does not vary. So the broadband noise takes little longer to grow, as we have already talked. Now, what happens to the protection to the very loud sound? The next topic of discussion today is if it's an impulsive, strong, very powerful sound, then how do we get a protection? So, first, let's look at the sound which is not so impulsive, the sound which is continuous in nature, the kind of experiments you do at home and maybe in the laboratory. And this kind of experiment I can suggest you also to do. So put your headphones, but remember, be very, very careful. So put your headphones, put a tone generator app, keep your sound of your mobile phone to minimum, put the frequency at around 500 hertz, and then slowly increase the volume. Remember, do it slowly. You increase the volume one step, wait for 10 seconds, allow your ear to adapt, and then go on increasing. Now, once you increase the volume, you will find that initially nothing is audible, then sound will start becoming audible, and then as you increase the volume further, you would realize that there is a sensation of pain. Once the sensation of pain comes in, the protection mechanism kicks in. We normally called it as acoustic reflex, and it can kick in anywhere when the sound intensity is above 80 or 85 dB, depending on person to person. So around 80 dB above or 85 dB above, the acoustic reflex kicks in. Now, what is acoustic reflex? Simple to understand. What happens is your muscles around the eardrum, they become taut. When they become taut, the eardrum pulls in this side, and that actually pulls this entire bone and hammer structure behind, and that helps your sound, that actually stops your sound effectively to reach to the cochlea. Now, typically, this offers a reduction in the sound for about 20 dB. So, if you are playing your note at around 85 dB, then you will find that because of this, at a higher volume, your ears will contract, and suddenly you would realize that the sound you are hearing is not so loud. There's typically a 20 dB drop, and this 85 dB sound will actually feel like a 65 dB sound. So that is the acoustic reflex. Remember, I did tell you that if you want to try the experiment, you can do that, but do it very slowly. There is a reason for it, and the reason is simple. This acoustic reflex, which is a mechanism derived or designed to protect the ears from a permanent damage by a very loud sound, kicks in some time. It only starts after 30 or 40 millisecond after the sound has risen to 80 or 85 dB. So the moment the sound has risen to 85 dB, it takes around 30 to 40 millisecond for the brain to decipher and give instructions and the muscles to start contracting. The complete contraction and complete protection takes even some time. Maybe it can go up to 200 millisecond. So your protection to ears is not 100% foolproof. If it's a very loud and very impulsive sound, very loud means suppose your the sound is maybe around say 100 dB, and it's very impulsive, maybe around say 20 milliseconds. So you have a very loud sound lasting for around only 20 milliseconds, then it is too late to prevent the injury to the ear, or maybe not 20, maybe 40 or 50 or 60 millisecond. Remember, 20 millisecond, the ear will not even sense the loudness, but around in 50 or 60 millisecond ear will sense the loudness, but it is not enough for the reflex action to kick in completely and the injury to the ear can happen. So that kind of shot noise, gun noise, very loud and impulsive sound could be very much harmful. So typically, if somebody shouts in your ear very close, it could be very harmful. Or if you are in an industry, in a um, place like airport where the loud sounds are expected, these things can happen. And that is why one has to put a preventive note. So there are suggestions like if there are going to be a dynamite blast, many sites where the road building or airport buildings or dam buildings are happening, they require a lot of dynamite blasts, which are these kind of loud impulsive sound. So obviously the engineers do wear those this thing, headphones or whatever, to protect, head cups, they won't be headphones, to protect them from sound. But sometimes it is suggested that you have to or you must run a preventive note or a preventive sound of a say 100 dB or something, a continuous sound, so that your reflex action also kicks in even before the loud impulsive sound comes. So suppose if you have a 90 dB note played for say 2 seconds, then your reflex action is always in place, and then the blast happens, then maybe you will be saved. This kind of things are um usually played when you take a, I mean, a parallel thing I'm talking, happens when you take a nighttime photograph of a human being. So you know that if in the dark, if you take a photograph, the flashlight blinks many times. Why does it blink many times if there is one photo? The answer is simple. The eye pupil get dilated in the dark, and if lot of light comes in, then the eyes are reflected from the backside, from the retina, and that gives the retinal image in the final photograph, which we call as red eye. So what happens is generally the cameras give multiple flashes. The last one is for taking the photo, but the flashes before that kicks in the im- kicks in the reflex action in the eye, so that the your eye lens diameter reduces and it allows very less light to come in. So that is the preventive note happens. Adaptations, yes, this is one adaptation as I have discussed to you. Human ear has got this reflex action which offers a 20 dB adaptation to the large, impulsive, damaging sound. Now, ear is a remarkable device as we had argued earlier compared to human eye. But as far as this adaptation is concerned, human eye is better. Human eyes has created eyelids, and if you have a very intense light, then they simply close the eyes so that no light can enter. Of course, still some light can enter, but light intensity drops drastically if you close the eyelids. On contrary, adaptation for human ear is not so strong. It's just minus 20 dB and it is slow. So why such a thing has happened? Answer to this question may lie in the fact that the large impulsive sounds are very new to the world. Like large impulsive sound. Remember the gunpowder was discovered in some medieval period, 1300, 1400, and large industrial premises came only after industrial revolution. So in last 700-800 years our surrounding has become much more noisier, and these kind of impulsive sounds are there. But life before that, maybe before say 1000 AD, it was much peaceful. There were hardly any sources, there were hardly any industrial sources of loud noise, and therefore over the period of time or period of evolution, the adaptation to harsh sound has not an inbuilt thing in human ear. Maybe with time we can grow those ear lids as we have eyelids. So yeah, so here, so if there's an ear lid, it will cover from here. Maybe, you never know. But that's large time in evolution. Evolution happens over millions of years. We are we won't be living till then. Anyway, let's come to the some of the problem solving. So you can take out your pen and paper and go ahead with the first problem. I will read it, give you some hint, and then I can wait so that you can put the answers on the screen. We have some time, so we can do it easily and in a relaxed manner. Which will sound louder? A pure tone LP, P is small, LP, the sound pressure level, remember, not sound intensity level. LP of 40 dB at 2000 hertz, or a pure tone of sound pressure level 65 dB at 50 hertz, which will sound louder, a 40 dB at 22,000 hertz or 65 dB at 50 hertz. So recall in the beginning of or in the last lecture we discussed this, where we said that the perception of loudness varies with position and with frequency. So, and I had shown you a graph. So you don't have to go back and check this graph. I have here, I'm presenting it for you. This is the curves of equal audibility or equal loudness. Um, Sound pressure level on y-axis, frequency on x-axis. Now looking at this graph, let me see if you can answer this question. Which will be sound, which will sound louder? A pure tone of 40 dB at 2000 Hertz or a pure tone of 50 Hertz at 65 dB? So yeah, I mean Roshni has given answer 40 dB, 2000 Hertz, and look at the graph carefully and let us see what do we get here. Riddhiman is saying 40 dB. So let me also just check if anyone else has to say anything. Look at this graph carefully. 50 Hertz is here. 65 dB will be between 60 and 70. 2000 Hertz is here and 40 dB is here. So Rishabh says, Akshita says, everybody is saying 40 dB. Let me also explore along with you. So, uh, 40 dB at 2000 Hertz. So, I am in the line of 40 dB. So, and 2000 Hertz. So, I will take this. So, I am right now here, or I'm just above, marginally above this loudness. Remember, these are the curves of equal loudness, means all the points on this curve, the loudness is same, the loudness perceived is same. I am just above this line here. Okay, let me figure out where does 65 dB and 50 hertz lie. So 50 hertz is here and 65 will be in the middle. So let me just go ahead, up, 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 up. This is 60 and this is 65. Perhaps this line which is crossing here, maybe it's almost at the center. So this is my loudness curve for 50 hertz, 65 dB. Now if I go and close toward this side, you will find that this curve is slightly less than 40 dB at 2000 hertz. So you can see that even though it is 40 dB at 2000 hertz, it will be slightly more loud. 40 dB 2000, you are at this you are at this intersection. 50 hertz 65 dB, you are at this intersection. If you bring it here, you will find that this is slightly less. So 40 dB at 2000 hertz will be slightly louder than 65 dB. Remember, it's much more sound pressure level, but at a lower frequency. Do remember this, because this problem illustrates the problems or challenges of designing loudspeakers or speakers simply at lower frequency. Even though the sound pressure is high, it does not sound that strong. So think about it. We will come back to this talk once again when we talk about speaker designs. Okay, let's go to the next one. How is it possible for one sound to mask a sound that has already occurred? Backward masking. Remember last class we did talk about backward masking. So backward masking means if you play one note, then you play the second note after the first note immediately. Then what happens is the second note under some conditions may mask the first note. Speculate what might happen in the human nervous system when such a phenomena occur. So can anyone tell me the answer to this question? Can anyone remember? It's a speculation, so nobody is asking to you to be very correct scientific. So do a speculate. Give me some speculation to talk about. If you remember, we did speak about this in the last class about the masking. Persistence of sound. Well, it's a reverse persistent Riddhiman. What it tells you that the next sound is masking the previous one. Namish, Namishka, the brain picks out the frequency from the sound that was heard before. No, remember this is backward masking. So the sound which is heard later, that is dominating than the previous one. Stimulus for the louder sound will be felt. Yes, obviously. But if you take two sounds, yes, so if the second sound is louder, maybe it dominates the first sound. So, what might be happening at the nervous system? We have discussed something about the cells, etc. So, maybe a loud sound might be disturbing the large number of cells, and if it if human hair cells are uh, Gamma is saying hair cells are larger in number for higher frequency. Yeah, that may happen. So higher frequency, if you recall the frequency response curve, then you saw that the frequency response curve has a long tail, and the previous note, if it is not strong in intensity, then the previous note's frequency response can get hidden into the next one. So that could be one of the reasons that the preceding sound may be masking the previous sound. It could be louder, or it could be such that the frequency response is covering the previous note. Yeah, so let's go ahead. This is a speculation. You read more, speculate more. I leave that to you. What sound pressure level is required to produce minimum audible field at 50, 100, 500, 5000, 10,000 hertz? Minimum audible field. So again, for this you need that graph, and I'm presenting it once again. Look at the graph and just give me the answer. You can write your answer as 50 dash and then whatever sound pressure level. Forget about 10 power, forget about this multiplication here. You just write this. So for 50, whatever is your minimum sound pressure level. And you can approximate the figures as well. No issues. 50 is 46. So let's see, let's have a look. So you have at 50 hertz, the minimum audibility is this, maybe the dotted line, but that is threshold. You can take that. So for 50 hertz, the threshold goes here. So for 50, it's around 45. That's right. And then you can go ahead in the same fashion. For 100, how much would it be? So check out and also find out how the audibility is decreasing. Yeah, Akshita, 40. It's slightly more than 40, I can say. For 50 hertz, the minute 40 is below the hearing threshold, so around 45. Yes. And then for 100, what would it be? 100 is 25. So if you are at 100, 100 is here. You can see that the minimum audibility threshold of audibility drops. So it's around 25. So look at the wonder. I mean, you are at 50, lower frequency. The instruments, speakers, everything has to work at a high pressure to make you hear. As you increase, it drops. For 500 hertz, and it drops to around 7. That's correct. 7 dB. And we can go ahead quickly now. You all can finish it fast. For 1000 hertz, you are at the middle. So that is around 5 decibel. And at 5000, you can see that it even drops further. It drops to around 6.6. No, sorry, -2. Yeah, -2. So very, very less. And at 10K again, you can see that it increases. So you have your audibility thresholds. The purpose of doing this exercise, that if you're listening to music, if you're listening to different kind of instruments, one has to take care that there are high frequency instruments like a guitar or a violin, and there are low frequency instruments like tabla or dholak, and both type of instruments hearing constraints are different. So one you hear at a very low frequency in a different way, one you hear at a higher frequency. Human voice generally goes in this range, 200 hertz, maybe 150 hertz to around 500 hertz. This is the range for the human voice. Okay, going ahead, I have one more problem with one violin. We took the name of violin, violin arrives. With one violin playing, the sound level at a certain place is measured as 50 dB. Remember, I'm talking about sound intensity level. I'm not talking about pressure level. Be careful. When I'm saying sound intensity level, I'm talking about sound intensity. Sound level, it is sound intensity level. When I'm talking about pressure level, then it is pressure level formula. There were two formulae. So, yeah. So, one violin playing 50 dB of sound. If you recall that if four violins playing equally loudly, what would be the sound level most likely to be at the same place? So, if you recall that famous movie Titanic, when it was sinking, there were violinists who were playing the violins, and I think there are four in three or four in number. If anyone knows exact number of violinists, perhaps can uh, point it out, or we can talk about that. So I just wonder how loud they were, and how loud were the other sounds in the surrounding. But that is a very important criteria. So what happens when? How do you solve this problem? That instead of one, now you have four. Sorry. So let's wait at this problem. So do remember that, just to recall the solution, do remember that intensities add up. If you are careful, let me give you a 1 minute talk here. The sound, if there are two uncorrelated sound, no interference taking place, nothing, we will simply say that intensities add up. Okay, and go ahead and solve our problem. Unless there is an interference, you know what happens when the interference takes place. When the interference takes place, then you get a maxima, you get a minima. Maxima get, suppose if you have two intensities of I and I, the maxima becomes 4I and minima becomes almost 0. So yes, it becomes an issue. Then these intensity addition will not apply. So be careful when you are applying or when you are solving such problems. So here I just assume that there are no pure tones, there are no interference happening. Each violins are playing independently and their sound simply adds up. So now think. Here, as I said, intensities will add. Amplitudes don't add. Amplitudes undergo principle of superposition, which is under root of a1 square plus a2 square plus a3 square or whatever. Intensities are the square of the amplitude. So if you square amplitude equation, you will get a simple addition. That's how the intensities will add. But intensities in dB will not add. Do remember. If the four violins are playing, then it's not that 50 plus 50 plus 50 plus 200. No, it will not happen that way. So how do you solve? So from 50 dB, you find the intensity first, and then you add it for the four violin, assuming are all identical. You can say 4 times intensity and then calculate the dB once again. So please do that. So you can write 50 is equal to 10 log I by I0. So 0 will cancel. It will give you 5 log, remember, to the base 10 I by I0. and then you take anti-log of both sides. Anti-log of 5 must give you, I guess, 10 power 5, which will be equal to I by I0. I0 is 10 power minus 12 multiplied to 10 power 5 should give you 10 power 7. So, so I0 should turn out to be 10 power 7 if I'm not incorrect in my oral calculations. And now you have four violins playing, so that will add up 10 power 7 plus 10 power 7 plus 10 power 7 plus 10 power 7. So four of them will give you uh, 4 into 10 power 7, and again you divide by 10 power 12, sorry, minus 12, and do solve again. How much you are getting, Pratham? 56 dB. That's right, that's right. The answer is 56 dB. There's a shortcut to this solution. So remember, I think while discussing the logarithms and dB scale lecture before last, I did talk that if the intensity gets doubled, the you get a 3 dB gain. Recall it. If the intensity gets doubled, you almost get a 3 dB gain. Remember, log 2 is 2.3.101, something like that. So almost 3 dB gain. So look at it. From one violin, if you go to two violins, you will double the intensity. So that's 1 3 dB gain. Now this is four violin. So from two violins, if you go to four violins, you will double it once again. Doubling it once again will give you one more 3 dB gain. Yeah. Sorry. So, so you double the violins, you double the intensity here two times, 1 to 2 and 2 to 4. So you get 3 dB gain twice. That will give you a 56 dB. That's right, Rishabh. This is Nokia. Yeah. Expert people, huh? Take the next problem. Let me see what is the expertise. Find the sound pressure and the intensity of a sound with LP is equal to 50 dB. So this is pressure level. I just give you the relevant formulae that will keep your life straightforward. Just to recall, the pressure level formula is 20 log P by P0. Again, this is sound pressure LP. P stands for sound pressure. Level L stands for level, P for pressure level. It's 50 dB. So you are going to use this one. I'm just asking you to recall in the theory we have done and do remember. And maybe by evening today I will put your assignments. So there also these kind of problems will appear. Practice them too. And by the end of it, you should be a champion in solving acoustics problems. 20 log P by P0. So wonderful, you got LP, that will give you P. P0, remember, is 2 into 10 power minus 5. So what do you get as pressure? Can you tell me? 2 pascals. Cool. I put 50 here. 0 cancel, you get 5 by 2, which is 2.5. Take anti-log, 10 power 2.5 into, I guess everyone gets the same answer. What about your intensity? So intensity, you know, is P square upon rho into C. Once you get P from this one, put it in this equation. What is rho C? So what is rho here? Yeah, it looks incorrect, Atharva. You can make your correction and give me the final figure. I'm waiting. I can make out some oral calculation. So it will go in decimal. Yeah, something like that. Yeah, in Pascal. That's right. 6.32 into 10 power minus 3 Pascal. Once you get your pressure, then you calculate P square divided by density of air and the velocity in air. Now recall, you can put the values density of air or and velocity of sound in air, but recall in the lecture I had told you that this product is around 110, 120. Sorry, 410, 420. Instead of taking at them 410 or 420, depending under which condition of pressure, uh, and we see that we take this as a round figure of 400 for solving problems. Okay, so intensity is P square divided by 400. Okay, so please do that. That's right, 6.32 millipascal. That's correct. Go to this one, divide, make a square of it. So that will give you around 40 into 10 power minus 6 divided by 400. So that should give you 1 by 10 or zero point 0.1 into 10 power minus 6, or that could be around 10 power minus 7. That's right. That, and its intensity, remember, put proper units. That's right, Akshita, watt per meter square. Now again, if I'm not asking it here, but suppose if you have to calculate in dB, then you divide by I0, take log, multiply by 10, and you get intensity in dB. That's how you will convert uh, uh, sound pressure level to sound intensity level. That's how the complete conversion will happen. You know, I divided by I0, take a log of to the base 10, multiply by 10, and you get uh, sound intensity level. Oh, okay, that's right. That was the last problem. So you can convert into sound intensity level and check it for you. Now with this or with these problems and today's topic, I finished chapter 6. Next lecture, I plan to start with chapter 7. Thank you. I will be coming to the Google Meet uh, in 2 minutes, and anyone who has doubts or discussion, please come there to talk about it. Attendance link I'm going to post on the WhatsApp group.